Hello everyone, my name is Harnit Saini. I am Assistant Professor in Akgec Engineering College. Today the topic of discussion is set theory. Right? Let's start with set theory. Now, a set is a collection of well-defined distinct objects. These objects in a set are called the elements or the members of the set. The name of the set is written in uppercase, like A, this way, right? And the name and the elements of the set are written in the lowercase. If X is an element of the set A, we say that X belongs to or X is a member of A and is expressed symbolically as X belongs to A, right? If Y is not the member of A, then this is symbolically denoted as Y doesn't belongs to A. Let V be, now we can say here, let V be the set of all the vowels, then V is written as, V will be in the capital case because it is the name of the set, and the elements A, E, I, O, U will be in the smaller case as they are the members of the set. The curly brackets denoting the beginning and end. Whenever we put these curly brackets here, it is denoted that this is the starting of the set and this is the end of the set, right? Now, representation of the sets, we can represent it in various ways, right? In this first is the roster method. In this form, all the elements, all the members of the set are listed. These members are separated by the commas and are enclosed in braces like 1, 2, 3, this way, right? We will separate all these with the commas and we will, beginning and end, we will put the curly brackets. This is a set roster form. For example, the set of counting numbers from 1 to 5, we would be written as like this. Set builder form of a set. In this form, a set is defined by stating the properties which are satisfied by its elements. Here the rule governing the membership of the set is stated. Now here we will not write the members, but we will write the rule. Rule for which all the members will be satisfying, right? The rule is true for some of the members and that will be included in the set. For example, a set of all even positive integers is written in the set builder form, like B, X is such that X is an even positive integer, or we can put this symbol or this symbol, right? And now the members of this set will be the all even positive integers, right? Now some other special sets are the null set or the empty set. Means this is a set with no elements and often symbolized by the symbol phi, right? Universal set, the set of all the elements currently under consideration and is often symbolized by capital U, right? This means there is no element in the set. This means that all the elements are included in the set, right? Now, when we are writing phi is not equal to curly bracket phi, because phi means nothing, but if we put a curly bracket, then this means that there is an element in the set. Maybe it is a null element, but there is some element existing in the. Now the cardinality, right? If S is a finite, if S is finite, then the cardinality of S is symbolized by this absolute value of S is a number of distinct elements in S. Means the element, if we count the number of elements in a set, that is the cardinality, right? Now we can see here in this S there is 1, 2, 3 elements, then the cardinality is 3. In this case we can see that there are number of elements, but they are all same. We will count only once, right? So this can be repeated any number of times, but the element will be in cardinality, we will count it once. So the cardinality of this set is 1. Again we have written phi with no curly bracket, that means there is no element in it. Now in this we can see that 1 element, 2 element and 3 element. There are 3 elements in this set. This is the starting braces, this is the ending braces. In this we can see here these are the 3 elements, so the cardinality is 3. If S is equal to this 0, 1, 2, 3 up to infinity, then the cardinality is infinite in this case, right? Singleton set, a set containing only one element is called a singleton set. For example, A is equal to 3. Now 3 is the only element here, and in B there is only element 0 here. So that's why these sets are called the singleton sets, right? Now, null set or the void set or empty set. A set which contains no element is called a set. It is denoted by symbol this one, or we can even make it empty curly brackets, right? This also symbolizes that there is no element in the set. Now, example of the null set, if we want to write in set builder form, the set of integers between 9 by 4 and 11 by 4, there is no integer in between these numbers. The set of integers that are less than 4 and greater than 8, not possible at all. So there is no number in that. The set A is equal to x, x square is equal to 16 and x is odd. Okay, when we are squaring something and we are getting 16, that means x is equal to plus 4 or minus 4, right? So it cannot be odd anytime. So this is also not true. So that means there will be no element in the set. The set of persons of age greater than 400 years. According to the study, there is no person can be alive up to 400 years. So this is also not true, and that means there is no element in this. The set of married bachelors. A bachelor is a person who is not married. So this is also not true, and that means there is no element in this. Right? Now the finite and infinite sets. A set is called a finite if it has n distinct elements where n belongs to n. Such a set consists of specific number of different elements. It means we are able to count those elements. That is called a finite set. In such a set, the process of counting different members come to an end. Otherwise, a set is infinite. We give below the examples of such sets. A set of positive integers greater than 4 and less than 11 is a finite because it has 6 elements, 5, 6, 7, 8, 9, 10, and can be counted. So we are able to count it. So that means it is a finite set. Like A is equal to 2, 4, 6. This is an infinite set because we don't know where these even numbers are ending, right? So it is an infinite set. X is an Indian citizen is a finite set because we can count the population of India, right? Now what is a subset? If A is a subset of B, we write the symbol will be using like this way. A is a subset of B to designate that relationship. If A is the proper subset of B, we write the symbol just like this only to designate the relationship. If A is not the subset of B, we write this way and we will cut it like this and like this to designate that relationship. Now, what is the meaning of subset? Subset means all the elements of A are contained in B, right? Is the proper subset means A is contained in B and B is also having some other elements other to A, right? Which is A is not the subset of B means none of the element of A is there in B, right? Now see here, a set A is 1, 2, 3 and is a subset of B because in B 1, 2, 3 this whole A is contained here and other elements are also there. So this is called a subset. A is called the subset of A. B because A is contained in B. B contains all the elements of A. We write A is a subset of B to designate this relationship between A and B. we could also say that 1, 2, 3 is contained in or is a subset of the 1, 2, 3, 4, 5, 6, right. Another example, the set A is 3, 5, 7 is not a subset because we have 7, we have 5, but we do not have 3 here. So it cannot be a subset. For a subset, all the elements of the first set should be contained in the second set. So here we cannot say that A is a subset of B, right? Because 3 is an element of A, but it is not the element of B. The empty set is a subset of every set. This is the point to remember, that empty set is a subset of every set because every element of the empty set is an element of every other set, right. Now subset one more. If this way also you can write A is 1, 2, 3, 4, 5 is a subset of, now one is written in the roster form and other is written in the set builder form. X is less than 6 and X is a counting number, means counting number means it is an integer, right. Now less than 6, all of these elements are satisfying this condition. So that means these elements are contained in this. We can say that A is a subset of B. Notice also that B is a subset of A because every element of B is an element of A. We can say that if you take it reversibly and at B is X less than 6, any element less than 6, and here in A if you check, you can see that all these elements that are satisfying this situation is condition, are present here, right. So we can say that A is a subset of B and B is also a subset of A, right. Now what is a superset? If A is a subset of B, then B is said to be the superset of A. This relation is written as B is the superset of A, which reads B contains A or B is the superset of A, right. Now if we are writing that A is a subset of B, now B is the then superset, right. So we can also write B is the superset of A, right. So these both the equations are equal, right, means the same. Two sets A and B are equal if A is a subset of B and B is also subset of A. If the two sets A and B are equal, we write A equal to B to designate the relationships. This means that the elements of A are exactly same to the elements of B. Now you can see the example. The sets A has 3, 4, 6 and B has 6, 3, 4 are equal because all these elements are contained in B and all these elements of B are contained in A, right. Maybe their position are here and there, but the element is there. So this means that the two sets are equal, right. Now we can have another example. If A, we have discussed this also in the previous slide, like A is having elements 1, 2, 3, 4, 5 and B is the having the condition X less than 6, right. Now X is the counting number, then A is the subset of B because every element of A is contained in B and B is also the subset of A because this condition, all the elements that are satisfying this condition are contained in A. So we can say that A and B are equal, right. Now what is the power set? If S is the set, then the power set of S is the set containing all the subsets of given set S, as its element is called the power set of the S and is denoted by 2 raised to power S or PS is equal to 2s, right. Now you see, when the set is given, all the possible subsets we can make out of that set, right, and we make the set of the subsets, then it is the power set. Like you can see that S is equal to A. A is having only one element, right, and the power set is phi will always be included. We know that the phi, the empty number, is the subset of all the sets. So we have to include this, and secondly, there is only one element, so we will write it here, right? Now you can see here the cardinality, only one element is there, 2 raised to power 1, the 2, and so in power set there will be 2 elements, right? Now if there are 2 elements, right, see whatever the subsets possible, phi will be there, only A, only B, and both. Then you can see here 2 elements, 2 raised to power 2 is equal to 4. See, in the power set there are 4 elements, right? Similarly is the case with S is equal to phi and this one, right? Now you can see here this is different to this one, right, and different to this one also. So we have to include this again here, right? If S is finite, then 2 raised to power S is equal to 2 raised to power cardinality of S. We know that we are doing here. If there is one element, the cardinality is 2 raised to power 1. If there are 2 elements, cardinality is 2 raised to power 2. Similarly in all the cases. Now what are disjoint sets? If no element of A is the member of B and no element of B is the member of A, and B are said to be the disjoint sets. Like if A is equal to 1, 2, 3, B is equal to 4, 5, 6, right? No element of A is here and no element of B is here. So these are disjoint sets. But if 1 or 2 elements are similar in there, then we cannot say that they are disjoint sets, right? In such a case, 2 sets A and B have no elements in common. If we put here 6, then 6 will be common in both the sets. So they are not equal, but they are not disjoint also, because one element is common in both, right? So we have to take care of that. Now comparability. 2 sets A and B are said to be comparable if A belongs to B and B belongs to A, or A is equal to B. When we are to perform any operation on the sets should be comparable to each other, and they are only comparable if they are equal to each other, right? Now A and B are not comparable if A is not the subset of B and B is not the subset of A, right? And means A is not equal to B. In this case, there will be at least one element in each set which not a member of the other set. Example of comparable, like A is XYZ, B is this one. Now A is the subset of B. Okay, we got one condition, right? Then A and B are comparable as A is the subset of B. Now if A is 2, 3 and B is 3, 4, 5, then A and B are not comparable, because we cannot write A is a subset of B or B is a subset of A. We cannot write both, any one of this. So, or we cannot write A is equal to B. So these, out of these 3 conditions, at least one condition should be true, then only these sets will be comparable. But we, in this case, we are not able to write this. So these A and B are not comparable in this. Now see the various operations. First is intersection of the set. The intersection of the 2 sets A and B is a set of all elements which belong to A and B both. Means we have to take out the common elements. If we are saying that the intersection of the 2 sets has to be written, then we have to see that what elements are common in both these sets. Like, okay, and the symbol for this is A intersection B, right? The intersection of A and B is also written as like this, A intersection B. That means X belongs to A and X belongs to B, right? And we can also write it like this, X belongs to A and is replaced by the AND symbol, and X belongs to B also, right? Difference of the set, right? The difference of the two sets A and B is a set of elements which belong to set A but do not belong to set B. This is denoted by A minus B, or A, this curly dash, B, or A slash B is read at A's difference B or A minus B. Now, the difference of the set A and B is also written as A minus B. That means X belongs to A and X doesn't belongs to B. Or this AND symbol can be replaced by the AND word is replaced by the symbol. Now we can see the example. If A is equal to 1, 2, 3 and B is equal to 2, 3, 4, let's suppose, then A minus B, right? We have to subtract all the B elements from here, like 2 and 3 will not come, only 1 will come, right? A minus B is 1. All the elements of A that are not in B, A minus B is there, right? Complement. The complement of set A is the set of the elements which do not belong to A. It is therefore the difference of the universal set and the set A, and the complement of A is denoted by A dash or A complement. That means A complement means X doesn't belong to A. You can see the example. If you say that universal set is 1, 2, 3 up to 10 and A is equal to 2, 3, 4, then A complement will be all the elements of the universal set which are not in A, means 1, 5, 6, 7 up to 10, right? This is the meaning of this complement. Now there is another operation called symmetric difference A, symmetric difference B, then X. Here the elements are X belongs to A and X doesn't belongs to B, or X belongs to B and X doesn't belong to A. Means we have to include both the elements of A and B by cutting the common elements. That means we have to exclude the, first we have to find out the union of A and B, and then we will exclude the intersecting elements, means common elements from both, right? And if we want to solve it, that A minus B and B minus A is the union. Now I will tell you with the example. If A is equal to 1, 2, 3, B is equal to 3, 4, 5, right? Then A symmetric difference B is equal to, first we will take the union and we will not take the common element, right? This way. This is a symmetric difference, and A minus B is what? Only 1 and 2, right? We will only exclude the element which is in B, but in A symmetric difference B we will include both the elements of A and B, but we will exclude the intersecting elements, right? A multi-set aka BAG and M set are the modification of the concept of a set that, unlike a set, allows multiple instances of each of its elements, right? In a multi-set we can have multiple instances of the same element again and again. The element A has a multiplicity 2 because it is written 2 times in the set, and B has multiplicity 1 because it is written 1 time in this. In the multiset, this A is having the multiplicity 3 and B is also having the multiplicity 3 because they are repeated 3 times in that set. Then these sets can be represented in the form of Venn diagrams also, right? A Venn diagram is a pictorial representation of the sets. U is a universal set which is represented as a rectangle. This rectangle is the U. This rectangle is the universal set, and the other sets are represented as circles. Now there is 2 sets A and B, right? This means that the element of A are contained in B. Like if we are drawing like this universal set, this is set A and this is set B. All the elements of the universal set are divided into A and B. And if we are having intersection, then we can say that A, B. This is the intersection part, means the common part between the two, right? This is the union part, A union B part, right? A this way. This is the, here we can say, here we can combine these both, right? If we are wanted to have this A union B, right? This way, this means A is a subset of B. All the elements of A are contained in B. See? Right? And subset of B contains this situation, right? More on Venn diagrams, we can say the set of integers, set of rational numbers, set of real numbers. These all are subsets of each other, right? Thank you very much.